morning, all the participants, and very warm welcome to respected Dr. Paresh Patel, sir, beloved lecturers, and dear students. I, Khushbu Desai, once again heartily welcome you all for an exciting session on symmetry and group theory in chemistry and its applications. It's our privilege that Dr. Paresh Patel, sir, is again joining with us for today's webinar. In the last lecture, he had given excellent subject knowledge. So, everyone learned a lot and benefited from your lecture. Thank you very much, sir, for your amazing lecture and discussions. Now, I request Paresh, sir, to continue further with today's session. Over to you, sir.
Good morning, all of you. Good morning, Dr. Khushbu and Desai, madam. Uh, and good morning, dear students. Okay, in the first lecture, we discussed the general introduction regarding the molecular symmetry and group theory, point groups. Today, we are going for the symmetry, group theory in chemistry and its applications. Uh, The syllabus of this topic, as per as our Veer Narmad South Gujarat University prescribed syllabus, first title is the representation of a group, representation of a matrices, and matrices, matrix notation for the geometrical transformations, orthogonality theorem, and its important consequences, reducible, irreducible representations, and relationship, preparation of character table for C2V, C3V point group, and applications of the group theory, transformation applications of group theory, transformation properties of the atomic orbitals, and sigma bonding. This is the syllabus of our topic. So, dear students, first of all, we are going for the matrix. Now, matrix is a combination of the numbers arranged in a rectangle array and combination with the another matrix, and matrix can be represented as a numbers of the rows and numbers of the column. So, dear students, first of all, what is matrix? Matrix is a combination of the numbers and arranged in a rectangle array as a numbers of the rows and the numbers of the column. So, let us start with the matrix. So, dear students, first title of our topic is matrix. Now, what is matrix? Matrix is the combination of the numbers arranged in a rectangle array and rectangle in form of the numbers of the rows and numbers of the column. So, matrix can be represented by m by n. M is equal to numbers of the rows and numbers of the column. So, anyhow, what is matrix? Matrix can be represented as a combination of the numbers which can arrange in a rectangle array as the numbers of the rows and numbers of the column. Now, in case of numbers of the rows and numbers of the column, this is the first column, a first row of this matrix, and this is the first column of this matrix. This is the second row of this matrix. This is the second column of the matrix. So, anyhow, matrix can be represented as a numbers of the rows and numbers of the column. E11 represents first element of the first row and first column. E12 that represents this element is the first row and the second column of this matrix. A13, this is the element of the first row and the third element of this matrix. A21, this is the element of the second row and the first column of this matrix. And finally, AMN, it means this is the element for the mth row and nth column of the matrix. So anyhow, matrix can be represented as a numbers of the rows and numbers of the column. M represents numbers of the rows and N represents numbers of the column. Now dimension of this matrix. Dimension of this matrix is nothing but the numbers of the rows and numbers of the columns. 1, 2, 2, 3. B is equal to 1, 2, 2, 1, 3, 0. C is equal to 1, 0, 3, 2, 4, 5. So matrix A, here number of the rows is equal to 2, 1 row, second row, and numbers of the column also 2. So this matrix can be represented as a 2 by 2 matrix. In case of matrix B, 1, 2, and 3 rows and 2 columns. So this matrix can be represented as 3 by 2 matrix. Now matrix C, here number of the rows is equal to 2, numbers of the column is equal to 3. So this matrix can be represented as 2 by 3 matrix. So anyhow, dimension of the matrix can be represented as a numbers of the rows and numbers of the column. Summation and subtraction of matrices. Summation and subtraction of matrices are possible if the numbers of the rows and numbers of the column are the same, or we can say dimension of both these matrices are the same. Then and then summation and subtraction can be possible. As for example, matrix A is equal to 2, 4, 2, 4, 5, 4, 3, 2, 3, 1, 0. Matrix B is equal to 1, 2, 5, 2, 1, 0, 2, 0, 0. Now A plus B, summation of matrix A plus B can be represented as 2 plus 1, 4 plus 2, 5 plus 5, 4 plus 2, 3 plus 1, 2 plus 0, 3 plus 2, 1 plus 0, 0 plus 0. So is equal to 3, 6, 10, 6, 4, 2, 5, 1, 0. So this is the summation of two matrices. The summation of any two matrices is possible if the dimension of both these matrices are the same. Similarly, if you go for the A minus B, subtraction of matrix A from B. So similarly, subtraction is also possible if the dimension of both these matrices are the same. So 2 minus 1, 1, 4 minus 2, 0, 2, 2, 2, 1, 1, 0. So subsection and summation and subsection of any two matrices are possible if the dimension of both these matrices are the same. Next one is combination of any two matrices. Combination or multiplication of any two matrices is possible if the numbers of the rows of the first matrix is equal to numbers of the column of the second matrix, or number of the rows of the second matrix and number of the column of the first matrix, then and then combination can be possible. As for example, A is equal to 1, 3, 2, 2, 1, 0. B is equal to 1, 3, 2, 0, 1, 0. Now here, number of the rows of the first matrix is equal to number of the column of the second matrix, then and then combination can be possible. So here, number of the rows in the matrix A is equal to 2 and number of the column is equal to column B is equal to 3. It means here combination can be possible. If you go for the combination of A cross B is equal to number of the first row, first column. It means we have to go for first row and first column. So combination of 1, 1 is 1 plus second element of the first row, second column, and first column and second row. First column and second row plus 2 into 1. Okay, so overall result is 1 1 za 1, 3 2 za 6 plus 2 1 za. It means total answer is 1 plus 6 plus 2. It means 9. So first row, second column. 1 1 3 za plus 0 plus 2 0. So overall result is 3. Similarly, we have to go for the second row and second column. Three twos are 6. Answer will be plus 0 0. Second row, second column. Second row, second column. It means 3 twos are 6. 3 threes are sorry. So second row, first column. It means 2 ones are 2. 1 twos are 2 plus 0. It means answer is 4. Then second row, second column. Answer is 6. So this is the combination of two matrices. The number of the rows of the first matrix is equal to number of the column of the second matrix. Then and then combination or multiplication can be possible. Now, how to find out the determinant of this matrix? Now, to find out the determinant for the matrix for the 2-dimensional and 3-dimensional, Both are the different. In case of the two-dimensional, A is equal to 5, 3, 2, and 1. 5 and 3 can be represented as a diagonal position of the element or diagonal elements. This is 2 by 2 dimension matrix. In case of determinant of this matrix is nothing but the combination of the diagonal elements minus other than diagonal elements. Okay, so how to find out the determinant for the two-dimensional matrix? Combination of diagonal elements minus combination of other than diagonal elements. So determinant matrix A is equal to 5 ones are 5 minus 3 twos are 6 is equal to 5 minus 6 is equal to minus 1. So in case of the two-dimensional matrix, to find out the determinant of this matrix is nothing but the combination of diagonal elements minus combination of other than diagonal elements. So this is the two-dimensional matrix. In case of the three-dimensional matrix, A is equal to 3, 1, 2, 1, 2, 1, 3, 4, 0. This is three-dimensional matrix. Here numbers of the rows and numbers of the columns is equal to 3. Now in case of the determinant of this matrix, this is the element of the first row, first column. So determinant of this matrix can be represented as a 3. Now remaining matrix can be represented as 2, 1, 4, 0 minus 1. This is the element of the first row and second columns. So remainings are 1, 1, 3, 0. 1, 1, 3, 0. Plus 2. This is the first row and third element. So remainings are 1, 2, and 3, 4. Now this is the two-dimensional matrix. So 3, 0 minus 4, minus 1, 0 minus 3, plus 2, 4 minus 6 is equal to 3 minus 4 minus 1 minus 3 plus 2 minus 2 is equal to minus 12 plus 3 minus 4 is equal to minus 13. Answer is minus 13. So this is the to find out the determinant for this is the determinant of the three-dimensional matrix. To find out the determinant for the two-dimensional matrix, we have to go for the combination of diagonal elements and minus other than diagonal elements. In case of the three-dimensional matrix, this is the method to find out the determinant of this matrix. Now, how to find out the character or trace of matrix? Character or trace can be represented as a symbol chi. Now, A is equal to 215, 312, 105. This is the matrix A. Now, what is the character or trace of this matrix? So, character of this matrix, this can be represented as a chi, and character is nothing but the summation of diagonal position of the element or diagonal elements. Okay, so character or trace of this matrix is equal to 2 plus 1 plus 5 is equal to 8. So character can be represented by summation of the diagonal elements, and character or trace of matrix can be represented by char. Now next title, and this title is important for our exams, that is types of matrices. First type of the matrix can be represented as a row matrix. Now, what is row matrix? A is equal to 1, 2, 4, 5, 4. Now, what is row matrix? Row matrix, number of the rows is equal to 1, and n number of column can be represented as a row matrix. As for example, A is equal to 1, 2, 5, 4. Second one is column matrix. A is equal to 2, 1, 5. So in case of the column matrix, number of the row, m number of the rows, and only one column can be represented as a column matrix. Third type of the matrix is diagonal matrix. Now, what is diagonal matrix? The values for the diagonal position of this matrix has some definite values, and the values for the other than diagonal elements are 0. So this type of the matrix can be represented as a diagonal matrix. Fourth one is unit matrix. The values for diagonal position of the elements are 1, and the values for other than diagonal elements are 0. So this type of the matrix can be represented as a unit matrix. Fifth one is singular matrix. A is equal to matrix A. Now determinant of this matrix is equal to 16 minus 16. So determinant of this matrix is equal to 0. Okay. What is singular matrix? If the determinant of the matrix is equal to 0, so this matrix can be represented as a singular matrix. Now last matrix is null matrix. A is equal to 0, 0, 0, 0. Now what is null matrix? If the value for the all the elements are 1. So this matrix can be represented as a null matrix. So these are the different types of the matrices. Matrix can be classified into row matrix, column matrix, diagonal matrix, vector diagonal matrix, then unit matrix, null matrix, and singular matrix. Now we are going for the how to find out the inverse of the matrix. Now to find out the inverse for the two-dimensional matrix and three-dimensional matrix, both are the different. To find out the inverse for the two-dimensional matrix, as for example, A is equal to this is two-dimensional matrix. Now how to find out the inverse of this matrix, that is A inverse. Now it involves 4 stages. First stage, to find out the determinant of this matrix. Okay, we know that determinant of this matrix is equal to 16 minus 15 is equal to 1. This is the first step. To find out the inverse for the two-dimensional matrix, first step is to find out the determinant of this matrix. Second step, change the position of the diagonal elements. Okay, so these are the two diagonal elements. Change the position of the diagonal elements. So we have to change the position of the diagonal elements. So values are the same. So 4 and 4. Next stage, third stage, change the position of other than diagonal elements. It means minus 5, minus 3. This is the third step. And fourth step, divide each element of the matrix by the determinant of this matrix. So 1, 1, 1, 1. So after all, 4 minus 3 minus 5 and 4. So this is the inverse for the two-dimensional matrix. So dear students, how to find out the inverse for the two-dimensional matrix? First of all, we have to find out the determinant of this matrix. Second step, change the position of the diagonal elements. And third one, change the sign of other than diagonal elements. And last step, to divide each element of the matrix by the determinant of this matrix. So this is the this is the inverse for the two-dimensional matrix. Now how to find out the inverse for the three-dimensional matrix? To find out the inverse for the three-dimensional matrix is different from the previous one. So in this one, A is equal to 143, 210, and 132. Now this is three-dimensional matrix 143, 210, 132. Now first step, to find out the determinant of this matrix, A is equal to 1, 1, 0, 3, 2. First row, first column, minus 4. This is the element of the first row, second column. So remainings are 2, 0, 1, 2 plus 3. This is the element of the first row, third column. So remainings are 2, 1, 1, 3 is equal to 1, 2 minus 0, minus 4, 4 minus 0, plus 3, 6 minus 1 is equal to 2 minus 16 plus 15. So is equal to 1. So determinant of this matrix is equal to 1. This is the first step to find out the inverse of the matrix. of the three-dimensional matrix. Now, second step, to find out the values of C11, C12, C13, C21, C22, C23, C31, C32, and C33. Now, what is the value for C11? C11 is equal to minus 1 raised to m plus n, and remaining, that is the value. So, in case of C11, number of the rows is equal to 1, number of the column is equal to 1. In case of C11, this is the element of the first row, first column. So remainings are 1, 0, 3, 2 is equal to minus 1 raised to 2, 2 minus 0 is equal to minus 1 raised to square. It means plus 1. 2 minus 0 is equal to 2. So values for C11 is equal to 2. Similarly, if we go for the C12, now what is C12? This is known as C12 is equal to minus 1 raised to first row and second column. So remainings are 2, 0, 1, 2 is equal to 4 minus, is equal to minus 1 raised to 3 and 4 minus 0 is equal to minus 1 raised to 3. It means minus 1 and 4 is equal to minus 4. So values for C12 is equal to minus 4. Now next one for C13. C13 minus 1. This is the C13. So minus 1 raised to 1 plus 3. First row and third column. So remainings are 2, 1, 1, 3 is equal to minus 1 raised to 4 is equal to plus 1. 6 minus 1 is equal to plus 5. So values for C13 is equal to plus 5. Similarly, if you go for the C21, 2 plus 1, and remainings are, this is C21 position. It means first column and second row. Remainings are 4, 3, 3, 2. Minus 1 raised to 3, it means minus 1 is equal to plus 1. So value for C21 is equal to plus 1. Similarly, if you go for the C22, so value is equal to minus 1. And if you go for the C23, the value is plus 1. And for C31, the value is 3. And if you go for the C32, minus 3, C32 is equal to 6. And value for C33 is equal to minus 7. So 2 minus 4 plus 5, 1 minus 1, 1, and minus 3, 6, and 7. So similarly, if we go for the C22, C23, C31, C32, C33, these are the values for C112, C33. So we can represent this value in form of the matrix 2, minus 4, 5, 1, minus 1, 1, minus 3, 6, and 6 and minus 7. Now A inverse is equal to adjacent A and divided by determinant of this matrix. So in this case, uh, adjacent A, it means we have to convert these rows into column, that is known as adjacent A, and determinant of this matrix is equal to 1. So 2 minus 4, 5, 1 minus 1, 1, minus 3, 6, minus 7, and divided by 1, or we can represent is equal to divided by 1 by 1. So is equal to 2, 1, minus 3, minus 4, minus 1, 6, 5, 1, minus 7. So this is the inverse for the two-dimensional matrix. Two-dimensional matrix can be represented as a numbers of the rows and the numbers of the column. In this way, we can find out the inverse of the matrix. Inverse for the three-dimensional matrix can be calculated. First of all, we have to find out the values for determinant of this matrix. Then find out the value of C11, C12, C13, C21, C22, C23, C31, C23, and then convert or the arrange number of the rows into column, that is adjacent A, and divide each element of this matrix by the determinant of this matrix. So this is the inverse for the three-dimensional matrix. So this is the first title of this matrix. What is matrix? Matrix can be represented as a numbers of the rows, combination of numbers arranged in a rectangle array as a numbers of the rows and numbers of the column. Then we also discuss about the different types of matrices. Different types of matrices. Matrix can be classified into rows, rows matrix, column matrix, diagonal matrix, unit matrix, singular matrix, and last one is the null matrix. Then we also discussed how to find out the inverse of the two-dimensional matrix and three-dimensional matrix. Now we are going for the one single title, that is order of a group. Order of a group can be represented by small h. Now what is order of a group? Order of a group is nothing but the numbers of symmetry elements are present in a molecule. Order of a group is nothing but the numbers of symmetry elements are present in a molecule. As for example, first molecule is water molecule. We know that water molecule consists E, C2, sigma Vxz, and sigma Vyz symmetry elements. So here, number of the symmetry elements is equal to 4. So in case of the water molecule, order of a group is equal to 4. So remember, dear students, water molecule consists 4 symmetry elements: E, C2, sigma Vxz, and sigma Vyz. It means number of the symmetry elements for water molecule is equal to 4. So order of a group for water molecule is equal to 4. Second molecule is ammonia molecule. Ammonia molecule consists E, C3 plus or C31, C3 minus or C32, sigma Va or sigma V1, sigma Vb or sigma V2, and sigma Vc or sigma V3. So numbers of these symmetry elements are present in a ammonia molecule is equal to 6. So order of a group for ammonia molecule is equal to 6. Third one, In case of the BF3 molecule, symmetry elements E, C3 plus, C3 minus, and C3 is perpendicular to 3C2s, sigma H, twice S3, and 3 sigma V. So in case of the BF3 molecules, numbers of the symmetry elements is equal to 12. 1 plus 2, 3, 3 plus 6, 7, 7 plus 2, 9, and 3, 12. So order of a group for what BF3 molecule is equal to 12. Okay, so dear students, order of a group is equal to numbers of the symmetry elements are present in a molecule. So in case of the water molecule, order of a group is equal to 4. In ammonia molecule, order of a group is equal to 6. And BF3 molecule, order of a group is equal to 12. Now next title is how to find out the class or how to go for the similarity transformation. Suppose A, B, C, D, X. These are the symmetry elements of a particular group. If X inverse A into X is equal to A, this is the first conjugate properties. Second one is X inverse A into X is equal to B. And third one, X inverse A into X is equal to B. And X inverse B into X is equal to C. So here, three conditions are there. If A, B, C, D, X, these are the different symmetry elements of a particular group. Now, it satisfied the condition number 1. It means X inverse A into X. This is the inverse symmetry operation of X. X is nothing but the symmetry element of a particular group. So X inverse, it means this is the inverse symmetry operation of X and combination with A and X, answer will be the A. It means A is conjugate to A itself to form an individual class. So dear students, remember that if X inverse A into X is equal to A, it means A is conjugate to A itself to form an individual class. X inverse A into X is equal to B. It means A and B conjugate to each other to form a combined class. So dear students, remember that if X inverse A into X is equal to B, it means A and B conjugate to each other to form a combined class. And third conjugate property is X inverse A into X is equal to B and B inverse X inverse B into X is equal to C. It means A, B, C conjugate to each other to form a combined class. In case of A and B, A itself and A, B, C conjugate to one another to form a combined class. Okay, so these are the three conjugated properties. So A, B, C, D, X. These are the different symmetry elements of a particular group. Now, if you go for the symmetry operation X inverse means this is the inverse symmetry operation of X into A and X is equal to A. It means A is conjugate to itself to form an individual class. Second one, X inverse A into X is equal to B. It means A and B conjugate to each other to form a combined class. And third one, X inverse A into X is equal to B. x inverse B into x is equal to C. It means A, B, and C conjugate to one another form a combined class. Okay, so these are the conjugate properties. Now here, over here, x inverse A into x is equal to B. So B is the similarity transformation of A by symmetry operation x. Okay, what is similarity transformation? In second conjugate properties, B is the similarity transformation of A by symmetry operation x. Okay, B is the similarity transformation of A by symmetry operation x. Now, in case of water molecule, we know that water molecule consists E C2 sigma Vx sigma V yz symmetry operation. In this case, E is conjugate to itself to form an individual class. C2 conjugate to itself to form an individual class. Sigma V xz conjugate to itself to form an individual class. And sigma V yz conjugate to each other to form a combined class. Individual class. So in case of the water molecule, number of the classes is equal to E, C2, sigma Vxz, sigma Vyz. So numbers of the classes is equal to 4 in case of the water molecule, and with the help of this conjugate property we can prove it. So E is conjugate to itself, C2 conjugate to itself, sigma Vx conjugate to itself, and sigma Vyz conjugate to itself. Okay, in case of ammonia molecule consists E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. 6 symmetry elements are present in the ammonia molecule. Now, in this case, E is conjugate to itself to form an individual class. C3 plus C3 minus conjugate to each other to form a combined class. And sigma Va, sigma Vb, sigma Vc conjugate to one another to form a combined class. So, in case of the ammonia molecule, numbers of the classes is equal to 3. 1, 2, and 3. Okay, so remember, dear students, water molecule consists 4 symmetry elements and numbers of the classes is equal to 4. And in ammonia molecule, number of the symmetry elements is equal to 6, but the numbers of the classes is equal to 3. E is conjugate to itself to form an individual class. C3 plus C3 minus conjugate to each other to form a combined class. And sigma Va, sigma Vc, sigma Vb, sigma Vc conjugate to one another to form a combined class. So, in case of the water molecule, symmetry elements of the water molecule satisfy the condition number 1. And in case of the ammonia molecule, E can satisfy the condition number 1. C3 plus C3 minus conjugate to each other to form a combined class. So C3 plus and C3 minus can satisfy the condition number 2, and sigma Va, sigma Vb, sigma Vc can satisfy the condition number 3. Okay, so how to find out the class for the water molecule? We know that water molecule consists E, C2, sigma Vx and sigma Vyz symmetry elements. Okay, with respect to E, E inverse E into E, C21 inverse E into C21, sigma Vx inverse E into sigma Vx, sigma Vyz inverse A into sigma Vyz is equal to. Okay, we know that if we operate identity symmetry operation on any molecule, answer will be the same. So E inverse E into E is equal to E. Okay, now in case of the second one, C21 inverse. This is water molecule. If you go for the C21 inverse or C2 inverse, C21 inverse or C2 inverse, both are the same. Now C21 or C2, it means one time clockwise rotation around 180 along the main principal axis. So if you go for the C21 inverse, it means we have to go for the anti-clockwise rotation along the main principal axis, but answer will be the same in case of the water molecule, H1, H2. Then identity. So again, answer will be the same, H2, H1. And then C2, so answer will be the 1 and 2, original position of this molecule. So this can be represented as a E. Similarly, if you go for the sigma V XZ inverse, okay, remember that in case of water molecule consists two types of the planes. One is sigma V XZ plane, another one is sigma V YZ plane. Now, in case of sigma V XZ, this is sigma V XZ plane. Okay, or we can say this is known as molecular plane. So if we operate sigma V XZ symmetry operation on water molecule, the position of the hydrogens are as it is. There is no change in the position of the hydrogens. Okay, so by operating sigma V XZ inverse, answer will be the same, that is 1 and 2. By operating identity 1 and 2, overall result is 1 and 2. So answer is the same. Now, if you operate sigma V YZ symmetry operation, now sigma YZ, in case of the water molecule, this is known as sigma YZ symmetry operation. So, if we operate sigma YZ symmetry operation to the water molecule, the position of the hydrogens will be the change. So 2 and 1. Okay, sigma V YZ inverse, answer will be the same as sigma V YZ. Identity 2 and 1. Again C2, 1 and 2. So overall result is the same. So in case of the first symmetry element, as an identity, if we operate different symmetry operation, so answer will be the same. It means this can satisfy the condition number 1, x inverse A into x is equal to A. It means E is conjugate to itself to form a individual class. So whenever we talk about the character table for C2V, E, C2, sigma VXZ, sigma VYZ. Okay. So first class for the C2V is identity. So in any character table, E conjugate to itself to form an individual class. So first class of the C2V point group is the identity, or we can say E is conjugate to itself to form an individual class. Now next symmetry element is the C2. So if we go for the C2, 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 and C2. And let us see what will be the result. So if we operate first E inverse C2 into E, answer will be the C2. Now next one, C2 inverse. C2 1 inverse. Okay, C2 1, it means we have to go for the rotation along the main principal axis around 180. That is clockwise. But it inverse, answer will be the same. But we have to go for the anti-clockwise rotation. But in case of water molecule, the position of hydrogens will be the change. Then again C2 or C21. So again 1 and 2. Again C21, 2 and 1. So overall result, you can see from the original molecule and oriented position. So this is nothing but this C2 or C21, C2 or C21. Similarly, if you go for the sigma V XZ, if we operate sigma v xz or sigma v xz inverse. Okay, if you operate sigma v xz, there is no change in the position of the hydrogen in case of water molecule, and it inverse answer will be the same. Again, we have to go for the C21. It means 2 and 1, and again sigma v xz. So there is no change in the position of the hydrogens. So overall result is the C2 or C21. Both are the same. Now, if you go for the sigma v yz inverse, so sigma v yz, which can bisect the molecule to change the position of this hydrogen 1 and 2. Again C2, it means 1 and 2. Again YZ, it means 2 and 4. So overall result is the C21. So second class of water molecule is equal to C2. It means C2 is conjugate to C2 itself to form an individual class. So second class in the case of the water molecule is the C2. Third one, sigma V xz. Sigma V xz. Sigma V xz. Sigma V xz. Now, what will be the product? It is we have to discuss. First, E inverse. Sigma V xz. Answer will be the sigma V xz. C2 1 inverse or C2 inverse. Both are the same. So 2 and 1. Then sigma V xz. If you operate sigma V xz, so there is no change. So 2 and 1 as it is. Then C2, again C2 1. So overall result is the same. Or if you operate sigma V xz, there is no change. Next, sigma V xz inverse. So there is no change. So overall result is sigma V xz. If you operate sigma yz, then 2 and 1, 2 and 1, sigma V yz 1 and 2. So overall result is sigma V xz. It means sigma V xz conjugate to sigma V xz to form an individual class. So third class for the water molecule is equal to sigma V xz. Sigma xz. And last one, if you operate sigma V yz, then it should be sigma yz. Okay, first one, that will be the same. C2 inverse. So 2 and 1, sigma V yz. So again 1 and 2, sigma C2 or C21, 2 and 1. So overall results can be represented as sigma yz. Similarly, if you go for the sigma V xz inverse, 1 and 2, sigma V yz, it means 2 and 1. Again, sigma V xz, 2 and 1. So overall result is sigma yz. And last one, if you go for the sigma yz inverse, 2 and 1, 1 and 2, again yz, 2 and 1. So overall result is equal to sigma V yz. So fourth class of the symmetry elements of the water molecule is equal to sigma V yz. So why? Sigma V yz conjugate to itself. So in case of E is conjugate to itself, C2 conjugate to itself, sigma V XZ conjugate to itself, and sigma V YZ conjugate to itself to form a individual class. So in case of the water molecule, numbers of the classes is equal to 4. Now another molecule is the ammonia molecule. Now in case of the ammonia molecule, we know that symmetry elements E, C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc. These are the 6 symmetry elements are present in this molecule. Now, in case of ammonia molecule, E is conjugate to itself. Sigma Va, sigma Vb, sigma Vc conjugate to each other, one another to form a combined class. Now, how to find out the numbers of the classes in case of the ammonia molecule? So, whenever we talk about the character table for ammonia molecule, 2C3 and 3C2. Okay, that means E is conjugate to form a individual class. C3 plus C3 minus conjugate to each other to form a combined class, and 3 sigma V. It means sigma Va, sigma Vb, sigma Vc conjugate to one another to form a combined class. Now, in case of the ammonia molecule, E inverse E into E is equal to C3 plus inverse E into C3 plus, C3 minus inverse E into C3 minus, sigma Va inverse E into sigma Va is equal to sigma Vb E inverse E into E is equal to C3 plus inverse E into C3 plus, C3 minus inverse E into C3 minus, sigma Va inverse E into sigma Va, sigma Vb inverse E into sigma Vb, sigma Vc inverse E into sigma Vc is equal to. Now, in case of E inverse E into E, answer will be the identity. Now, C3 plus inverse. Now, in case of ammonia molecule, suppose this one is 1, 2, and 3. If you operate C3 plus inverse, C3 plus inverse, it means, so C3 plus, it means one time clockwise rotation along the main principal axis. Okay, C3 plus inverse, it means anti-clockwise rotation around 120. So anti-clockwise rotation, it means 1, 3, and 2. Then identity. Answer will be the same as 3, 1, 2. And again C3 plus. Original molecule. So overall result is identity. So this can be represented as an identity. This can be represented as an identity, again identity, again identity, again identity, and identity. So in case of the ammonia molecule, E is conjugate to itself. E is conjugate to E itself to form an individual class, or we can say in case of the ammonia molecule, the first class is the identity. Similarly, if you go for the C3 plus and C3 minus, C3 plus, C3 plus, C3 plus, C3 plus, C3 plus, C3 plus. Okay. Now in this case, answer will be the C3 plus. C3 plus inverse, C3 plus, C3 plus. C3 plus inverse. This is the answer. Again C3 plus. It means one time clockwise rotation. So 1, 3 and 2. Again C3 plus. So answer will be the 1, 3 and 2. So here answer is C3 plus. Overall result is the C3 plus. If you go for the C3 minus inverse, then what will happen? C3 minus, it means one time clockwise, anti-clockwise rotation. C3 minus inverse means one time anti-clockwise rotation. One time clockwise rotation. C3 minus means one time anti-clockwise rotation. C3 minus inverse, it means one time clockwise rotation. So 1, 2, 3. 1, 2, 3. It means 2, 1, 3. Okay, C3 plus. It means again one time clockwise rotation. 1, 3, 2. And then C3 plus. Again one time rotation. 1, 3, 2. So overall result is nothing but the, just a minute. This is C3 plus. It means one time clockwise rotation. Again C3 plus. It should be C3 minus. So overall result is 3 to 1. So overall result is C3 plus. Now next one is sigma VA inverse. This is important. Sigma VA inverse C3 plus sigma VA. In case of the ammonia molecule, first rotation followed by the reflection symmetry operation. So to perform the reflection symmetry operation, we have to consider the original position before the rotational axis of symmetry. So in that case, sigma VA inverse. Okay, sigma VA. We know that shape of the ammonia molecule is a pyramidal. Okay, so if we take sigma VA, so the position of the hydrogen 1 remains as it is, and there is a change to be changed the position of the hydrogen 2 and 3. So position of hydrogen 2 and 3 are the interchange. So similarly, sigma VA inverse answer will be the same. So the position of the hydrogen 1 remains unchanged, and 3 and 2 are interchanged by operating sigma VA inverse. Then C3 plus inverse. C3 plus only. It means one time clockwise rotation. So 1 over here, 2 over here, and 3 over here. Then sigma VA again. This is important. Now rotation followed by the reflection symmetry operation. In case of ammonia molecule, rotation followed by the reflection symmetry operation. So to operate sigma VA, it means reflection symmetry operation, we have to consider the position before the rotational axis of symmetry. So actually sigma VA, it means we have to put a mirror on the sigma VA. But instead of this VA, we have to go for this one. Okay, and we have to put a mirror over here. So the position of 3 remains as it is. 1 and 2 are interchanged. So repeat again. Actually, sigma VA, it means we have to put a mirror, sigma VA, we have to put a mirror over here. So instead of this sigma VA, rotation followed by the reflection. So we have to consider the position of the hydrogen before rotational axis. So sigma V, so hydrogen 1 is there. So we have to put a mirror over here. So the position of the hydrogen 3 remains unchanged. 1 and 2 are the change. So anyhow, this is nothing but this is the position for C3 minus. Okay. Again, we have to go for this sigma VB to give same results. Over here, this is the same result. Okay, so we can predict that C3 plus and C3 minus conjugate to each other to form a combined class. It means second class for the ammonia molecule is equal to 2C3, that is C3 plus and C3 minus. So if you go for this C3 minus, similarly, we can go for the C3 minus, C3 minus, C3 minus, plus, plus, plus. So answer will be the same. So C3 plus and C3 minus conjugate to each other to form a combined class. Next one is the sigma VA. Now in case of E inverse sigma VA is equal to sigma VA. Now this is important. C3 plus inverse sigma VA C3 plus. So if you operate C3 plus inverse, C3 plus it means one time clockwise rotation, and C3 plus inverse it means one time anti-clockwise rotation. Anti-clockwise rotation it means 3, 1 and 2. Then we have to go for the sigma VA. This is again rotation followed by the reflection. It means we have to go for the sigma VA. So instead of here, we have to put a mirror over here. Sigma VA. Okay. So we have to put a mirror over here. So the position of hydrogen 3 will be unchanged. 1 and 2 will be the change. Now C3 plus sigma VA, again C3 plus. C3 plus it means 1, 2 and 3. So compare this and this. So position of hydrogen 3 remains unchanged. So this is nothing but this sigma VC. Similarly, if you go for the sigma C3 minus inverse, sigma VA, C3 minus. C3 minus inverse. C3 minus means one time clockwise rotation. And C3 minus inverse, it means one time clockwise rotation. So 1, 3 and 2. Now rotation followed by the reflection. So sigma VA, it means we have to put a mirror over here, but we have to consider the position of this hydrogen. So hydrogen 2 remains as it is. 1 and 3 are interchanged. So again, C3 minus. C3 minus means one time anti-clockwise rotation. So 2, 3 and 1. So compare this and this. So position of the hydrogen 2 remains as it is. It means this is nothing but the sigma VB. So here sigma VA, sigma V, sigma VA, and sigma V. So overall result is nothing but the sigma VA, sigma VB, sigma VC conjugate to one another to form a combined class. So in case of the ammonia molecule, third class is the sigma V. Similarly, if you go for the sigma VB, sigma VB, so here sigma VB, here sigma VB, C3 plus inverse sigma VB. It means C3 plus inverse. C3 plus inverse. It means one time clockwise rotation. 3, 1, 2. Sigma VB. Sigma VB. So hydrogen 1 as it is. 2 and 3 interchange. Then C3 plus. It means one time clockwise rotation. 1, 2, and 3. So here there is no change in the position of hydrogen 1. So this is nothing but this sigma VA, sigma VC. VB, VB, VB. So anyhow, sigma VA, sigma VB, sigma VC conjugate to one another to form a combined class. So overall result is sigma VA or sigma VB or sigma VC. So anyhow, the third class of the ammonia molecule is equal to 3 sigma V. So dear students, this is the to how to find out the class for any representations. We already discussed about the water molecule and ammonia molecule. So I think this is the enough for today's discussion. We will meet on the next session later on. So thank you very much for listening to me very silently. Thank you, Khushbu madam, and thank you, uh, KBS College, principals of the KBS College, for providing me these platforms. Thank you very much.
Thank you so much, sir, for facilitating such a positive learning environment. We really enjoy your session, and so we are eagerly looking forward for your upcoming session on this topic. My sincere gratitude to all the participants. We will back soon with upcoming session. Kindly note all the participants, a recorded version of this webinar will be available on YouTube channel of our college. So kindly subscribe our channel to get the recorded version of this and upcoming webinar. Okay, goodbye everyone. Have a nice day, and once again thank you very much Dr. Paresh Patel sir. Thank you.
Thank you.